Hello AP Physics C students, please have your problem set in front of you, and we're going to go ahead and get started. Let's actually backtrack. At the end of class last time we had been working on problem 3, and I realized after class that I went through the solution with the math part, but I totally forgot to go over part A, which is the diagram part, which is just as important. So if you just go back to problem 3, refresh your memory. We have this rod on the conducting rails. We're looking down at the situation. We give the rod a quick shove to the left, and we see what happens. And here we have to show the direction of the current and the direction of the magnetic force on the rod. So how do we do this? Well, remember, the way you first visualize this was imagining the protons, which are free to move around inside the conductor. Really, it's electrons. We're going to pretend it's protons. The protons that are free to move around inside. And so to help us visualize the current, visualize one of the protons that's inside the conducting rods. There it is. And remember, the whole rod is given a shove to the left. So all the protons inside are moving to the left. Inside the magnetic field, which is the magnetic field pointing, well, that's all these dots. The field is out of the page, so you do your right-hand rule. The charge is moving to the left. The field is out of the page. Each of these protons feels a force to the top of the page. There's the magnetic force that causes the protons to start to flow out of here, making this end positive and the other end negative, right? The protons are collecting on this end. They're leaving behind this end, and so it looks like the terminals of a battery. There's the positive terminal, there's the negative terminal, and then we trace the flow of the charges around. Protons are held against their will here. They're free to escape, to head towards the resistor to release their energy, and so the protons flow to the right, to the bottom of the page of the resistor, to the left, and then once they get to the rod, they're flowing to the top of the page around in a clockwise fashion. Now we have to figure out the direction of the magnetic force on the rod. So right now, we're looking at the rod as a whole. So before we looked at the individual proton to determine the direction of the current, now we look at the rod as a single object. We've got a current pointing at the top of the page. The field is out of the page. We do our right-hand rule. We feel the magnetic force is pointing to the right. But of course, we should have expected that, right? Because remember, if we gave the bar a shove to the left, it can't go on forever. Otherwise, we would produce electricity forever, and we're getting something for nothing. We know that the universe is going to try to remove that energy, and so it's going to pull it back to the right. So we should have suspected this anyway, but it's good verification. Okay, let's go ahead to problem 4 now. So you can go ahead and read problem 4, pause the video, do as much of it as you can on your own, then come back to see the solution. Okay, so first of all, you should recognize that the acceleration here is not constant. It's not uniform. We're given this function with respect to time, which means we can't just go ahead and do kinematics. Remember, that was how we started this whole thing with calculus way back when, that if we have a changing acceleration, we can't just do our usual kinematics equations. The first thing we have to do is recognize that acceleration is dv dt. And we have to rearrange and solve for a function of velocity. So if you got stuck on that part, or if you did that part incorrectly, pause the video, do it again, then come back to see what happened. Okay, so we rearrange dv equals a dt. We're going to integrate both sides. Left-hand side is, well, we're integrating, from v0 to vf, so it's delta v. The right-hand side, I didn't put the limits of integration there. We're integrating from 0 to 2.5 seconds. v0 just happens to be 0. It says she starts from rest as she's carrying her flagpole. And so we're really just finding the final velocity. So we integrate that, we put in the limits of integration, and just as a checkpoint, we should be getting the final speed as 4.06 meters per second. At that point, it's just a matter of putting into the equation EMF equals BLV, the motional EMF that we derived in class. That should get us the answer there given. Okay, what about the picture? Well, we're drawing it from the side. So here's our flagpole. It's moving to the left. Usually we call, to the west to the left, although it doesn't have to be, but let's just do it this way. And so if you did it a little bit differently, maybe you want to restructure yours. Traditionally, left is west on the page. We are looking at it from the side, and of course it's in the magnetic field produced by the Earth. Which way is the Earth's magnetic field point? Well, we know it points north, right? And so we're looking at it from the side, and to the west is to our left. Which way is north? That's going to be ahead of us. So the magnetic field lines are pointing away from us. Think that one through if you got that wrong, if you're confused about that, right? If this is our left, that's our west. That means the north is directly ahead of us, so the field lines are pointing away from us. And now it's just a matter of, again, visualizing an individual mobile proton inside the conducting rod of the flagpole. And so it's going to be moving to the left, it's a magnetic field out of the page, and so it's going to be, in this case, pushed to the bottom, so the protons will collect on the bottom edge of the pole, leaving behind a negative charge on the top. Alright, go ahead to problem 5, where you're going to do as much as you can, pause the video, come back to see the solution. Okay, let's go ahead to problem 5 now. So we're looking at it from the side, and to the west is to our left. Which way is north? That's going to be ahead of us. So the magnetic field lines are pointing away from us. And now it's just a matter of, again, visualizing an individual mobile proton inside the conducting rod of the flagpole. And so it's going to be moving to the left, it's a magnetic field out of the page, and so it's going to be pushed to the bottom, so the protons will collect on the bottom edge of the pole, leaving behind a negative charge on the top. Alright, go ahead to problem 5, where you're going to do as much as you can, pause the video, come back to see the solution. Sorry, sort of gave that away, although it's pretty obvious what to do first. It's just a straight up Ohm's law problem here to find the initial value of the current. Although, if you got 2.4 amps, you did something wrong. You should be getting 2.3 amps. See if you can figure it out. Alright, hopefully you realize that it's not just the 5 ohm resistance of the resistor there, but the bar itself offers 0.2 ohms, so really it's delta VB over REQ to get us the 2.3 amps. Alright, part B, just A equals sigma F over M. It's just the magnetic force we're worried about here, because remember, just to refresh our memories, we're looking down at the situation, right? When you're looking at these sort of pictures here with the bar laid across the wires, you're looking down at it, so it's resting on the wires. You don't have to worry about the weight or the normal force contributing. It's just going to be the magnetic force. As soon as you close the circuit, there's going to be a current flowing, and so the bar has a current inside a magnetic field. If there's a magnetic force, it's going to be ILV sine theta, of course, because it's not a moving point charge. It's a moving, it's a conductor with wire with a conductor in it. So you put your numbers in, theta's going to be 90 degrees, you should be getting 5.5 meters per second squared. What direction is the acceleration? Well, think it through, right? Trace the flow of the charges out of the positive terminal of the battery. You should get the charges that are moving to the bottom of the page inside the rod. And so in a field that's pointing out of the page, we know it's going to be forced to the left, which means the acceleration is to the left as well. So what happens here is when you close the circuit, the bar actually starts to accelerate to the left. This actually forms a way of launching this, and I'll come to that in just a little bit. Alright, for letter C, describe the motion of the rod. So now, again, we look at one of our individual protons inside the rod. We look at one of the individual protons, it's moving to the left inside a magnetic field pointing out of the page. It feels a magnetic force to the top of the page, which is interesting, right? Because from the current itself provided by the battery, and that's why this is different, there is a battery in this circuit, as opposed to the other circuits we've done before that haven't had a battery. Now there is a battery forcing the charge to the bottom of the page, but now each of those protons feels a magnetic force to the top of the page. That's opposing the flow. So what happens here? Well, if the protons are flowing to the bottom of the page, but the magnetic force is opposing that, pushing them to the top of the page, that decreases the current. If it decreases the current in this equation, the magnetic force decreases, so the acceleration decreases. And so while it's going to accelerate to the left, it will continue to speed up, but at a lower and lower rate of speeding up. That's kind of an interesting idea that we're going to come back to later on in this topic. Okay, so I actually have in class a way to demonstrate some of this. You might recall the other day when I was furiously trying to generate current by moving the bar across the magnets on the magnetic force accelerators to the lab volts. The current won't flow until I put the metal bar across the rails. Then as soon as I do, it completes the circuit, sort of like closing the switch here in problem 5. All of a sudden there will be a current inside the metal rod, and it will experience a magnetic force. It will accelerate across the rails, which is what's happening here in problem 5. This is known as a railgun, and it's actually a prototypes are being made right now by the U.S. military. And so I've attached to the Google Classroom post a quick YouTube video I'd like you to watch about the Navy and their experiments with railguns. It's a fantastic way of launching a missile or some other sort of projectile without the use of gunpowder. It's relatively quiet, it's relatively inexpensive, it's relatively cost efficient, and can provide great amounts of acceleration in a short amount of time. So you're going to watch that as well before moving on to the next video that I post as we go through more notes.